Have you ever tried writing down the exact value of square root of 2? You'll find it never ends. No repeating pattern. No termination. Just digits going on forever. But why is that? Today, we are going to explore the fascinating world of irrational numbers, numbers that simply can't be written as a fraction. And using a powerful concept you already know, prime factorization, we'll prove why numbers like square root of 2 and square root of 3 are irrational. Let's revisit the basics. A number is called irrational if it cannot be expressed in the form p divided by q, where p and q are integers and q is not equal to 0. Examples: square root of 2, square root of 3, and even pi. They have non-terminating, non-repeating decimals. Compare that with rational numbers like 1 by 2 or 0.5, which ends, or 1 by 3, which repeats as 0.333. Now let's dive deeper and use logic to prove that square root of 2 is irrational. This is done using a clever strategy called proof by contradiction. We assume something is true and then show it leads to a contradiction. Step 1. Suppose square root of 2 is rational. That means we can write it as a fraction a divided by b, where a and b are coprime integers. They have no common factors. Step 2. Now square both sides. Square root of 2 equals a over b, so 2 is a squared divided by b squared. Multiply both sides by b squared will be to b squared equals to a squared. This means a squared is divisible by 2, so a must be divisible by 2. So let's say a equals to c. Substituting that, a squared equals 4c squared. And to b squared equals 4c squared, so b squared equal to c squared. This means b squared is also divisible by 2, so b must also be divisible by 2. But wait. That means both a and b are divisible by 2, which contradicts our original assumption that a and b were coprime. So our assumption was wrong. Square root 2 is not rational. It is irrational. The same logic can be used to prove that square root of 3 is irrational too. Let's assume square root of 3 equals a divided by b, where a and b are coprime integers. Squaring both sides gives 3 equals a squared divided by b squared, or 3b squared equals 2a squared. This implies a squared is divisible by 3, so a is divisible by 3. Let a equals 3c. Substituting back, a squared equals 9c squared. 3b squared equals 9c squared. So b squared equals to 3c squared, which means b is also divisible by 3. Again, a and b are both divisible by 3, contradicting our assumption that they are coprime. Therefore, square root of 3 is irrational. In general, if p is any prime number, then square root of p is always irrational. Okay, but where do we see irrational numbers in real life? Geometry is one place. For example, the diagonal of a square with side 1 unit is square root of 2, and that's irrational. You also encounter irrational numbers in science, like the golden ratio and pi in physics, design, and nature. Knowing a number is irrational helps us understand its behavior, especially in calculations, measurements, and even coding algorithms. What about numbers like 3 plus square root of 2 or 1 divided by root 2? Turns out, those are also irrational. Let's try one. Suppose 5 minus square root of 3 is rational. That means 5 minus square root of 3 equals a over b, which means square root of 3 equals 5 minus a over b. But 5 minus a over b is a rational number. That means square root of 3 would also be rational, But we already proved that square root of 3 is irrational. So the assumption was false. Hence, 5 minus square root of 3 is irrational. The same logic works for numbers like 3 root 2 and 1 over root 2. Let's quickly recap what we've learned. Irrational numbers cannot be written as a ratio of integers. Square roots of prime numbers like square root of 2, square root of 3, square root of 5 are always irrational. We prove this using contradiction and prime factorization. Even combinations like 5 minus square root of 3 or 3 root 2 are irrational. Irrational numbers pop up in geometry, nature, and advanced math.